everyone. Thank you so much for joining me today. Today we're going to be looking at calculus. And you know, calculus is such a big topic. There's so much to cover. So let's get straight into it. So calculus is about 25% of your final exam, and it covers a lot of key topics that we're going to try and cover today. A few of them, not all of them, but we're going to try and cover quite a few of them today. So specifically, calculus looks at limits, differentiation from first principles, the rules of differentiation, equations of tangents to graphs, cubic functions, and optimization and maxima and minima. And today, let's look at what we are going to do. Specifically, we're going to look at limits. We're going to look at differentiation from first principles, rules of differentiation, gradient and equation of tangents. So by the end of the lesson, we're going to revise correctly using the limit notation and avoiding some of the common errors that creep up in exams. You know, with the pressure, we need to avoid certain things like careless mistakes. We're also going to look at correctly substituting values using first principles, apply rules for differentiation, and looking at simplifying expressions, specifically revising some of the exponent laws that we learned. And last, we will look at finding the gradient and equation of a tangent. Now, there's different ways that we can say find the derivative. And we're going to look now at some of the keywords that you can see in an exam paper. So the question might say something like differentiate, or it might say determine the gradient, or calculate the derivative, or find the rate of change. Guys, this is all clues that what you actually need to do is to derive, okay? So all these different ways are just indicating, and all these different words and different languages just indicating that you need to find the derivative of a function or an expression. So remember, we will be reminding you as we go through the lesson about these key terms and where you need to use it. Some of the common mistakes that I see cropping up during exam times, especially looking at exam papers, is learners tend to use the limit notation incorrectly in the first principles formula. I'm going to talk about this again in the lesson. There's also errors in substitution, and especially when we're looking at deriving by rule involving exponents and surds, we need to talk more about how you simplify those. When there's multi-step problems, we've got to be very, very careful not to misinterpret the question. So what should you be able to do by the time you get to grade 12 and start limits? Remember, calculus is actually only introduced in grade 12, but there are some key concepts that you need from grade 10 and 11. For example, exponents, algebraic expressions, substitution, and we will then look at how we apply that to the rules of differentiation. So the whole objective of today is to improve the way you perform in your exam. Of course, we're going to focus on how you think about things, how you manage your time, and some of the fundamental concepts that you need to be successful in calculus. And we'll pick that up right after this. Welcome back, everyone. I'm so glad that you stayed with us to find out more about calculus. So next we're going to talk about some key concepts that we'll be covering today. We're going to start off with limits, and then we'll move into differentiation and gradient and equation of a tangent. So some of the key problems that we see cropping up in limits is not being able to distinguish between the value of a function at a particular point and finding the limit. Now remember, there's a difference between a function value, so for example f of 0, and then finding the limit of the function at that point, which leads to the concept of finding the gradient at a point. We also see errors in substitution in limit problems, which I will take you through as we go through the first question. Very, very important for exams is to remember that you need to practice well in advance. You cannot wake up the week before your maths exam and decide, oh, it's time I start going over this content. You are not going to be in a position then to remember what each question is asking. If you have not consistently engaged with the material, you're going to struggle to recall and apply necessary knowledge during the exams. Some of the concepts that we need to remember from grade 10 and 11, substitution, this becomes important, especially when we look at limits, and then simplifying algebraic fractions. So these things are not directly tested in calculus, but you need to understand these basics so that you don't make careless errors. All right, so let's see what we're talking about here. Let's look at the first example. So we read the question, and we first need to understand what is the question asking. So the question says, find the limit as x approaches 3 of x squared minus 9 over x minus 3. So we see this in an exam, and we see we've got limit as x approaches 3. So that straight away already is my clue of what I should be doing and the steps I should be following. When I look at this question, I see that I need to simplify this algebraic fraction. Where's that concept coming in from grade 10 and grade 9? How do I simplify that fraction? I need to use factorization. How do we factorize this? Let's have a look at this and carry on with the example. If you were to, for example, substitute x approaches 3 and take that 3 and substitute it straight into this equation, x squared minus 9 over x minus 3, what would happen? The entire expression becomes 0 over 0, which is undefined. So this is why we have this idea of a limit, because it helps to tell us what's happening to a graph as x is approaching a certain value, and in this case it's as x is approaching 3. So to find the limit, we must first simplify the expression. Now remember, the limit is not the value of the function at the point. It's just telling you what's happening to the graph as x is approaching a specific value. So to answer the question, the first thing we do is we need to factorize x squared minus 9. It's a difference of squares. That's a concept we learn in grade 9. To factorize, it's the square root of x squared, which is x, minus the square root of 9, which is 3. And then it's the square root of x plus the square root of 3. Once we've simplified in that form, we can see now that we have common factors in the denominator and the numerator, so we can cancel those common factors out before we substitute the value of x is equal to 3. If you do it before you've cancelled out your common factors, you're going to end up again with 0 over 0, which is not going to lead you to the correct answer. So now we've got the limit as x approaches 3 of x plus 3. So at this point, we can now substitute the value of 3 in place of x, and we'll see that the limit as x approaches 3 is going to be equal to 3 plus 3, which is 6. Okay, so to answer the question, it says the limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. Again, I'll remind you that that is not the function value. It's just telling us that this graph is approaching a value of 6 as x is approaching 3. All right, guys. So what we're going to do now is we're going to move on to differentiation from first principles. So some of the key problems that we see in first principles is incorrect use of the limit notation when you use that first principle formula. Now, guys, there's absolutely no reason to get this formula incorrect. And the reason for that is because you get this formula on the formula sheet. What formula am I talking about? I'm talking about the first principles formula, which says the derivative of f with respect to x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And the problem that happens here in an exam setting is that learners sometimes take this limit and move it to the other side, or completely leave it out as you go through the question. This concept is so essential and important to calculus that if you leave that little phrase out, limit as h tends to 0, you're not even finding the gradient by first principles. So you have to include the limit as h approaches 0 through the entire question, which we're going to go through just now. Okay, so this formula, no need to get this wrong. It comes up in the formula sheet. Also, we're going to look at how do we transform expressions involving exponents and surds, and then interpreting the answer to the derivative. This part here we're mainly going to look at when we look at deriving by rule. But some simplification does come up in first principles. Really, what's important is to read to understand. If the question requires you to use first principles, it will tell you to use first principles in the question, okay? All right, so we need to remember how to simplify fractions, exponents, and surds, which we will go through later on in the lesson. Determine the derivative of f of x from first principles if f of x is equal to minus 3x squared. Now, let's read the question. Determine. Determine means find. Find the derivative of f from first principles. So key statements that they've given you here. First principles tells you that you need to use the formula, the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, what you can do, there's different ways you can set this up. The one way you can set this question up is to say, let's work out f of x separately, f of x plus h separately, and then bring it all back into the question right at the end. So I can find f of x plus h, and remember what you're doing here is you're replacing x, you're replacing the value of x with x plus h. So you're substituting. You see that concept again from grade 10. We're substituting the value of x plus h where we see x. Okay, so we put that into the bracket and then we simplify that by squaring that bracket out. All right, let's just go back there. So to simplify this, it's going to be equal to negative 3, square your bracket out, into x squared plus 2xh plus h squared. All right, then we multiply into the bracket, so we end up with minus 3x squared. Be very, very careful with your signs. Remember, negative times a positive is a negative. Concepts that we've learned in grade 8 already. Negative times a positive is negative 6xh minus 3h squared. So we've worked out f of x plus h. We've worked out f of x. Now we're going to take those values and put them into the formula we have to find the derivative from first principles. Okay, so let's do that. Let's move on to this one here. So we're going to say the derivative f of x is equal to the limit as h approaches 0, and now I start substituting my value. So it's f of x plus h. Remember what we saw. F of x plus h was minus 3x squared minus 6xh minus 3h squared, and then we said minus f of x, and f of x itself was negative 3x squared. And this whole thing is all over h. We now simplify by timesing this negative into the bracket. A minus times a minus is a plus. And what you'll see will happen is this first term will cancel out with the last term. So the terms without an h in them cancel out. It always happens, guys, in this way. I've been doing limits and first principles for a very long time. It always happens in this way. The term that does not have an h in it will cancel out at this step, okay? So we end up with, remember what I said, we need to keep this limit as h approaches 0. We keep that. That term and that term cancels out. It's plus 3x squared minus 3x squared. We get minus 6xh minus 3h squared all over h. We then simplify by factorizing and taking out a common factor of h. Remember, you cannot cancel across the minus sign. You cannot cancel across terms. So this is equal to the limit as h approaches 0 of h into minus 6x minus 3h all over h. And those cancel out. Now at this point, this is where we can substitute h is equal to 0. So therefore we get from first principles that the derivative of minus 3x squared is equal to minus 6x. Okay, so now when we get to this part, we ask ourselves, what have we found? What is this expression? What is this derivative actually telling us? So this expression that we found using first principles is giving us an expression to find the gradient of a curve at any point. So for example, if I wanted to know what is the gradient of this curve, minus 3x squared, at the point x is equal to 1. All I do is I simply take this expression, which we've got for the derivative, and I find the derivative at 1, substitute it in place of x, and I'll get minus 6. So that means we need to be able to interpret our answer. That means the gradient at 1 on this specific curve is equal to minus 6. All right? Okay, guys, we're going to move on now to rules of differentiation. So using first principles, remember your question will guide you to the fact that you need to use first principles. If the question says nothing at all, then we need to use the rules of differentiation. Important things that we need to remember when we are doing rules of differentiation is to simplify exponents and surds correctly. So we're quickly going to talk about that. And then we obviously apply the correct rules when we get into our question. Remember, this is just a reminder of what an exponent looks like. This is your exponent, that's your base, and the whole thing together is called a power. There are a whole lot of exponent rules that you need to remember that you've been learning since grade 8, okay? Exponent rules, for example, when we multiply powers with the same base, we add the exponents. I'm not going to go through all of these rules because these are concepts that you have already learned, but these are very important concepts for first principles. Also, just a reminder of a fractional exponent, which is what a surd is. If I want to change from a fractional exponent into a surd, have a look at this. We say if I've got a to the power m over n, this is the same as the nth root of a to the m. So what's happening? The numerator of the exponent is becoming the numerator of the exponent inside of the base. And then the denominator is becoming the root of your surd. Okay. Let's quickly go through this example. We want to find the derivative of the cube root of x to the power of 5. So what did I just tell you? The first important thing we've got to do is to rewrite the cube root of x to the power of 5. How do I do that? Remember what I said. I said the numerator went inside, so it becomes the numerator here. That's what went inside to become your exponent. And this number here in the root is what becomes your denominator. So we need to correctly transpose or transcribe this. So this would become x to the power 5 over 3. At this point, remember you haven't done anything because they're asking us to find the derivative. So we've rewritten from surd to exponential form. Now to find the derivative with respect to x, at this point, don't do this. Don't write this. This is incorrect. You do not show the simplification as part of the answer to the derivative. Your derivative must contain your final answer. Okay, that's not correct. So what do? We say, well, now we can rewrite this as the derivative of x to the power 5 over 3. That's what I'm looking for. And I can find the answer to that by using the power rule from the rules of differentiation. How do I do that? I take the exponent, multiply it by the coefficient in front of the x, which is 1. So it's 5 over 3 times 1. And from the power, we subtract 1. So my answer will be 5 over 3 times x to the power 5 over 3 minus 1 will give me 2/3. And that's my answer. Now you see what I've done here? I've only derived in this step once I've used the equal sign. Once you've put an equal sign in there, you cannot still be simplifying the expression. The equal sign indicates that you're getting to your final answer. All right, guys, so we've covered quite a bit. I think that means it's time for us to take a quick break. Hello everyone, thank you for coming back. So now we're going to move on to gradients and equations of tangents. And it's a concept that learners do struggle with a little bit, well, quite a bit. And it's mainly because you don't understand what the question is asking you. So some of the key problems that we see, not understanding what a tangent is. Remember, a tangent is a line that touches a graph. It can be any graph at just one point. Another mistake is using the average gradient instead of the derivative. Derivative, we're going to say it over and over again. Derivative gives us the gradient at a point. The average gradient, which is this formula here, this can only be used for straight lines. We do not track changes using that formula. When the derivative changes throughout the curve, we need to use this derivative and the point that we need to find the gradient of. Okay? So interpreting, we'll go back through how do we answer these questions, what is the question actually telling me? And a problem that you might find when you're actually going through the exam and you're sitting and you're looking at this paper is, well, I understand, but how do I express my answer? So we're going to look at how do you actually set your answer out so that the marker can mark. Because remember, you're doing your exam for the marker to mark it. So if they can't make sense of what you're saying, they don't have an opportunity to say, well, hello, what did you mean? So you need to express your mathematical reasoning coherently. And if we don't, unfortunately, that's where we can lead to lots of marks being lost. All right, guys, I quickly want to show you what we're talking about when we're talking about a gradient at a point and what this means on a curve. Okay, so don't worry about the curve we've drawn here. It's not a cubic function, it's another graph. But if you look at me moving this line, do you see that as I move this line, it's the same line, but it's changing? What's happening? What's happening? What's happening? The gradient is changing as we move the point of contact. So what happens? Is it the same line really? No. The equation of this line is going to change as you move this point to different sections of the graph, okay? And we can do this throughout the curve. But do you see how the equation changes? And why I wanted to show you this is because sometimes learners think, well, I found this equation of this tangent already. There's another tangent, it's got the same equation. It's not the case. Another tangent will look completely different. So it will have a completely different equation to the one you may have found that touches at the point x is equal 1. So if the point is x is equal to -1, the graph may even have a completely different inclination, okay? So it's just something to bear in mind and a way to visualize what you're actually doing. So let's have a look at this example. Remember, we read the question, we read to understand, we mark off key information. Find the equation of a tangent. Straight away, key things start coming into my head. If I'm talking about a tangent, which is a straight line, and I'm looking for the equation, I know that its ultimate form is going to be y is equal to mx plus c, which means I need the gradient and I need the y-intercept. Okay, so those are things that I already start marking down when I'm writing an exam in my head. You don't have to literally write it on your paper. Find the equation of the tangent to this curve, which is a parabola, at the point 3, 5. Now, what's very, very useful when you see a question like this is to draw a diagram. What exactly is happening? Remember, as I just showed you just now, visualize what's going on. This is our curve, x squared minus 4. We've got a tangent to this graph at the point x is equal to 3. So it's going to look something. Let's just see if I've got a straight line tool here. Not really. Okay, so it's going to look something like this. Okay, so you've got a tangent, which is supposed to be a straight line, touching this graph at the point x is equal to 3. I know that this equation is going to be of the form y is equal to mx plus c. How do I get the key points that I need for the equation of the tangent? What are those key points? I need the gradient and I need the y-intercept. To find the gradient, it's a topic we've been talking about so far, talking about first principles, talking about derivative by rules. We find the gradient by finding the derivative. So to find the gradient of this graph at the point x is equal to 3, I need to find the gradient of the function x squared minus 4. Well, how do I do that? We know that to find the derivative, we can do it by rules. The derivative of f of x is going to be equal to, using the power rule, we take the 2, multiply to the 1 in front. 2 times 1 is 2. From the power 2, we subtract 1. This is just a rule that you've learned. If it's something that you're not familiar with while I'm talking through it, it means we need to go back and become familiar with the material. We need to revise, okay? So the gradient of this function is 2x. The derivative of 4 is 0 because it is a constant. So this expression, and I've said this in the previous segment, this expression will help me to find the gradient at any point of this curve. Yes, it gives me the gradient of this tangent, but it will also give me the gradient of another tangent I can draw, say, perhaps there or anywhere else on the graph. Okay. So if I want to find the gradient at the point 3, what am I going to do? Well, I'm going to substitute this value 3 into my expression for the gradient, and I'll get an answer of 6. So therefore the gradient at the point 3 is 6. In y is equal to mx plus c, I already have m. What I need now is the y-intercept. I use this formula here, y minus y1 is equal to m times x minus x1, where x1 and y1 are your coordinates. This formula is given to you on your formula sheet. It sits in the analytical geometry section, but remember it comes up all over the place as you can see here. So y1 is our y value, the coordinate, so it's y minus 5, which is equal to the gradient, which is 6, times x minus x1, which is the x value of your coordinate, so it's going to be 3. And you cannot leave it at this point, okay? So we know that ultimately we want to write this equation in standard form, which is y is equal to mx plus c. So you cannot leave it here. We need to simplify further. Again, we're going back to concepts we learned in grade 9 and grade 10. Simplify this by expanding your brackets, timesing the 6 into your bracket. You get y minus 5 is equal to 6x minus 18. And then we're going to move the 5 over so that we get the final value for our y-intercept, which is the value c. So you get y is equal to 6x minus 18 plus 5. When I take this to the other side, remember the sign changes, is going to be minus 13. So therefore, let's understand what we found. We found, using calculus, that the gradient of this tangent is 6. And then we use that fact to find the equation of the straight line by substituting into the formula for the equation of the straight line. That's y minus y1 into m times x minus x1. So my equation y is equal to 6x minus 13 tells me what the equation of this specific tangent is at the point x is equal to 3. As I said, if we move through different points, the equation of that line, of a different line will be different. Quickly, let's revise the steps. To find the equation of a tangent, we find the derivative. How do we do that? We use the rules of differentiation. We are not going to be using first principles here. That's way too long. We want the quickest method, and that's using the rules. We substitute the x-coordinate of the given point to calculate the gradient. Okay, remember that's where we did the derivative at the point 3 in our example. We substitute the gradient of the tangent and the coordinates into an appropriate form of the straight line. You might go straight into y is equal to mx plus c to solve for the y-intercept. That's fine. I prefer the y minus y1, but there's no completely correct formula. You use the one that you are comfortable with, okay? And then finally, we make y the subject of the formula so we can write our equation in standard form. Okay, guys. Thank you so much for joining me. I know we've covered a lot of concepts. We've looked at limits, we looked at derivatives from first principles, derivatives from rules, we've covered a bit of exponents, and we've taken you through these concepts quite quickly just for you to be able to answer questions like the one about equations of tangents, which is really an application of the rules of differentiation. So we're going to start with looking at some practice questions, and this is from previous exam papers. I'd also like to give you some advice. One of the best ways to prepare for an exam is to do many past papers. Do as many as you can. This is going to help you with timing and pacing yourself. Remember that an exam is out of 150 marks, and what you want to aim for is at least a mark a minute. So if a question is, say, 10 marks, you don't want to spend more than 10 minutes on it. Use that as a guide for yourself. And you can only really pace yourself by practicing past papers. It's an important part of your preparation to write the final exam. Okay, so let's look at our first question here. We are asked to determine the derivative of f of x from first principles if f of x is given as 1 over x. So let's understand what the question is asking. They want us to determine, which means find. We are using first principles, which means there's a specific formula we need to use, and this formula is given to you on your formula sheet, so there's no need to get that one wrong. We'll look at the formula just now. You've got that the function f of x is equal to 1 over x. So certainly this type of first principles question is a little bit trickier because it has a fraction in it, but we follow the rules that we learned and we apply them consistently. Those rules don't change, and we will still get to the correct answer without panicking. Okay, so the formula that we're using for the derivative from first principles given to you on your formula sheet. It's the limit as h approaches 0 of f of x plus h minus f of x over h. You can straight away, if you feel comfortable, substituting f of x plus h. You can do that straight away in the numerator and replace f of x with 1 over x. Another alternative is you can list each one separately. So f of x is 1 over x, and you can work out what f of x plus h is by replacing x in your original question with x plus h. So you see, all I've done is I've replaced that denominator. X becomes x plus h. And then I can put these values into my formula and then attempt to simplify and find the derivative using first principles. All right. So let's continue with our example here. We've got the limit as h approaches 0. I'm just repeating the formula here. This is equal to, and this is where I'm now going to replace the values of f of x plus h. Remember, we saw that that was 1 over x plus h. And then we said minus f of x, and f of x itself is 1 over x. So once you've worked this out separately, you're simply substituting those values in. Also pay attention to the way we've set out the question. We're carrying the equal sign through and the limit as h approaches through the entire expression until we get right to the end where we find the answer and substitute to find the limit as h approaches 0. This entire expression is all over h. So another way to write this, because this is f of x plus h minus f of x over h, is to say this is times 1 over h. So this h in the denominator can be written as that. It's just to save you a bit of space on your page and to make it a little bit easier to work out your fraction. Okay, how do we simplify a fraction in this form? We have to find the LCD. LCD here is in brackets is going to be the product of x times x plus h. We multiply through, so we get x minus, in brackets, x plus h. I substitute the x plus h in brackets when I find the LCD. I'm timesing the 1 by the part of the denominator it doesn't have, which is x plus h. And this whole thing is multiplied by 1 over h. Okay, we simplify, so we're going to multiply the negative into the brackets. When you do this, you'll end up with, again, you keep the limit as h approaches 0 of x minus x. At this stage, when you've simplified, any term without an h will disappear. If your x terms are still there, so if you have right till the end of this question, you've still got an x in your expression, then you've made a mistake. So you've got to go back and check, okay? The terms without an h will disappear. So x minus x, gone. I multiply the negative in, negative 1 times h, so I end up with negative h all over my denominator, which is x times x plus h. And remember, this whole thing is times by 1 over h. We can now simplify. I've got an h in the denominator and an h in the numerator, so they cancel out. And I end up with the limit as h approaches 0 of negative 1 over x into x plus h. Now, it's at this point where you can replace your h with the value it's approaching, which is 0. So if this value here, we substitute 0, we end up with negative 1 over x times x, which is x squared. Okay, so therefore the expression that we get for the derivative from first principles of the function f of x is equal to 1 over x, the expression for the gradient ends up being negative 1 over x squared. Now what you need to do in an exam situation is do a quick check for yourself. Verify that the answer is correct. How do we do that? Quickly take the derivative of 1 over x by using the rules, okay? So I'm going to clear up some space on this slide by just erasing the stuff we don't need. I'll leave the answer on there. Okay, so let's do a quick check to see that our answer is correct. I know that from first principles I can simplify using exponents. 1 over x, using my exponent laws, this is going to be the same as x to the power of negative 1. Okay, and then if I find the derivative of that just by using the rules, my answer is going to be negative 1, take the minus 1, times it by the 1, x to the power minus 1 from the power, which is minus 2. But you're saying, hang on, that doesn't look exactly the same. No, it doesn't, because this has a negative exponent. So using your exponent rules, Remember, when you simplify, we try to write our answers with positive exponents. It will be minus 1 over x squared. We've changed our negative exponent to a positive, and these are exactly the same. So it's just a quick check, a quick way that you can see that your answer for first principles, which is usually about 5 marks, make sure that you get those 5 marks. It's just a straightforward application of a formula which you are given, and there's no need to write that formula incorrectly or misplace the limit when you are doing this question. Do a quick check by deriving by rules, make sure that your answers match up, and you can make sure that you then get a full 5 marks for this first question on derivatives. All right, let's move on to the next question. Again, we're looking at exam type questions. We're practicing getting our skills ready so that we can get these key marks in an exam, these marks that are easy for us to get. Okay, we are asked to determine, so again, we're finding something. Very popular word, always determining something in maths. Find the derivative of f of x if f of x is equal to 2x cubed minus 3x. Guys, remember to pay attention to what they're asking, and remember that if the question doesn't specifically say whether you should derive by first principles or derive by rules, then what you need to do is to derive by rules. So if there's no explicit instruction given, you are expected to use the rules to derive. So therefore, we know that I need to now use the power rule to derive this. I make sure that my expression is simplified. You see there's only separate terms here. There's no brackets, there's no roots or anything of that form, okay? So f of x is equal to 2x cubed minus 3x. The derivative of that, using the power rule, I multiply the 3, the exponent, by the coefficient of x cubed. So 3 times 2 is going to give me 6. Subtracting 1 from the power, so it becomes x squared. Same here with the minus 3x. Minus 3 times 1 is minus 3. X to the power 1 minus 1, which is 0. So it's x to the power of 0, which is 1. So therefore, my answer here is 6x squared minus 3. Okay, have we answered the question? Yes, we have. We read through, we make sure that we've used the correct rule that they wanted us to use, and therefore we know that we can score all the marks here provided we haven't made any careless mistakes. Another question on deriving by rule. Okay, this one again, another exam question, and it's using a concept that's critical in maths, and that's simplifying exponents and simplifying surds. Okay. In order for us to find the derivative here, so dx is simply saying we're finding the derivative with respect to x. The first thing we need to do, you see this one is written out a little bit differently than the previous one we did. We need to simplify this surd. How do we do that? We've got the cube root of x squared. So to get this expression in a form where we can find the derivative, we need to rewrite this with a rational exponent. The power inside stays as the numerator, and the 1 in the root sign becomes the denominator. So therefore, we first have to simplify the expression with the surd into an exponential form that we can now derive. So we've got the derivative is going to be taken of 7x. You see that I haven't started deriving yet. I'm just simplifying inside the bracket. Plus 2 times x to the negative 5. Okay, so we need to find the derivative of that expression. Once you start deriving, we don't half derive and then still keep a part of the expression. We need to derive the whole thing together. So the derivative of this is going to be equal to, when I now find the derivative, I leave this sign out, I leave the differential out, and we use our power rule. So it's 7 times 2 over 3 times x to the power 2 over 3 minus 1, which is going to give me minus a third. All right. Minus 5 times 2 is negative 10. X to the power negative 6. So we'll just tidy this up a little bit. So it's 7 times 2 is 14 over 3. X to the power negative a third minus 10 x to the negative 6. And the preference is really to write your answer with positive exponents. We would do that by moving these two expressions with x to the denominator. So this would become 14 over 3 x to the power a third. Okay, so I've changed my power from negative to positive by changing its position. Minus 10 over x to the power of 6. Again, rewriting my negative power with a positive power. Okay. So that's really taken us through the first 2 questions you get on differentiation in an exam. Deriving by first principles and then deriving by rule. By rules. Remember, those key concepts that we learn in grade 10 and 11 and grade 9 are so important, and that being how to simplify exponents and surds. All right, guys, let's take a quick break. When we come back, we'll practice some more. Hello everyone, welcome back. We are looking at practicing exams that are specifically related to calculus. We're going to be looking at we've already looked at actually questions involving differentiation, and now we're going to move on to equations and tangents. Let's look at what a typical exam question can look like. So the question says, determine the points on the curve, and you've given a function where the tangent is. Okay, so let's highlight key information here. Determine the point. So we're finding a point, which means it's an x and a y value. Often learners lose marks because they stop at finding the x value. But when the question says determine the point, you need an x and a y value. Okay, so we need to determine the point in the curve. This is a quadratic expression where the tangent is parallel to the line y is equal to 4t minus 2. Now, when a question is phrased in this form, I find that a diagram is very useful to help you list all the given information from the question. Okay, so we've got a parabola. They're saying that they want the equation of the determine the points. I must also read it nicely, and I'm telling you to read it nicely. Determine the points. So we're looking for x and y. We're not looking for the equation where the tangent is parallel to the line y is equal to 4t minus 2. So it means on this curve, we've got a tangent drawn at some point. We don't know what the point is because that's what we are looking for. And this tangent line is parallel. So do you see your analytical geometry concepts are coming in here? This tangent is parallel to another line. This line here has the equation y is equal to 4t minus 2. So when we're talking about parallel lines, the important concept that we learned from analytical geometry is that the gradients of parallel lines are equal. Okay, so the gradient of this line, that's nowhere near this curve, by the way, it's just parallel to the tangent. The gradient of this line is 4, and the gradient of this tangent, which is touching the curve, is also going to be equal to 4. Okay, we need to find the point of contact. So the question is phrased a little bit in a way that makes us think, well, what have we been given? What are we wanting to find? We have indirectly, do you see, we have been given the gradient, and we are asked to find the point of contact. So we're given the gradient. How do we calculate gradients in calculus? By deriving. I hope that that's what your answer was. So therefore, we need to take the derivative of h of t, and we then going to use the fact that we know that that gradient is 4 when the tangent makes contact with the curve. We're going to use that fact to help us find the coordinates of this point. Okay, so let's have a look at how we set this up. So h of t is 2t squared minus 1. Before I can derive that, I need to expand. Okay, so let's square our binomial. We end up with 4t squared minus 4t, square the minus 1, so it becomes plus 1. Now, in this form where we've got individual terms, separate terms, we are now in the position where we can derive. So we say the derivative now is going to be 8t minus 4. So that expression is the derivative for this entire curve, anywhere on the curve. And it's also the derivative that's going to help me to find the point of contact, because I know that the gradient here at this point with the tangent is 4. So we equate that to 4. Okay. And we're going to solve for t, t being I've written it here as x coordinate because that's what learners are familiar with, x and y. Remember, x is a variable. It can take on any letter. It can be k, it can be t, it can be anything. In this case, it's t. So therefore, we get 8t is equal to 4 minus 4. Bring that over to the right-hand side. It becomes a positive. So 4 plus 4 is 8. Therefore, t is equal to 1. Have I answered the question? No, because all I found is what we commonly know as the x value. So this is now the independent variable. So x is equal to 1. In this case, t is equal to 1. I need to still find the function value. How do I find the function value? I have to take this one and substitute it back into the expression for the function. So h of 1 is going to be equal to 2 times 1 minus 1 all squared. You see, I'm substituting into the equation that they gave me. I'm not substituting into the one I've squared out because it's quicker this way. All right. 2 times 1 is 2. 2 minus 1 is 1. 1 squared is 1. So therefore, what have I found? I found that this point of contact between the tangent and this parabola is the point 1, 1. Have I answered the question? Yes. I found the point where the tangent, which is parallel to this line, where it meets your curve. All right. So that's one way we can phrase a question on the equation of the tangent. We can relate that tangent to another line. Certainly, we've done the same thing in part B, but now we're relating it to a perpendicular line. The concept, though, is exactly the same as what we've done. It's just the analytical geometry that changes. So the calculus stays the same. It's only the analytical geometry concept that changes, okay? Remember that. So now we are looking at a tangent that's perpendicular to another line. So again, guys, remember, visualize this. Let's draw it, okay? We've got a tangent that's touching this curve. And this tangent is perpendicular to another line, okay? It might not be at the point of contact. It could be anywhere. It could be there. But this tangent is perpendicular to another line. They've given us the equation of this line as 2y plus t minus 4 is equal to 0. So here again, what we've done is we've written it in a form with the t. T is your independent variable. You're used to it as x, but it's really the same thing. These are all just placeholders, these variables. Why is this line, this perpendicular line, important? It's because it tells me something about the gradient. We learned from analytical geometry that the product of the gradients of perpendicular lines is equal to -1. Okay. So, how am I going to apply it here? I can rewrite this expression, 2y plus t minus 4 is equal to 0, as 2y is equal to -t plus 4. Divide through by 2, and I get y is equal to -1/2 t plus 2. So this perpendicular line, the gradient of that line is -1/2. And I know that the product of this line, the gradient, and the product of the gradient of the tangent, the product must be -1. So therefore, if this gradient is -1/2, what is going to get me to -1? -1/2 times the gradient of this tangent line is equal to -1. So therefore, the gradient of this t standing for tangent, not for the variable, the gradient of the tangent is going to be 2. -1 divided by -1/2 is going to give me 2. 2 times -1/2 is -1. All right? So therefore, this is the gradient of the tangent. I'm not interested now anymore in this -1/2. I've used it. It served its purpose. Do not by mistake take this and substitute it back into our gradient formula, because then we're going to make mistakes, okay? So it's a similar question to the one we've just done. We need to find the derivative, which we saw just now. The derivative expression was, let's just call it back up. It was 8t minus 4. Okay, so therefore we know now that this is equal to 2, because again we're trying to find the point of contact, so we're solving for t. 8t is equal to 6. We take the -4 over, it becomes positive. So t is equal to 6 over 8. Simplify that. Both of them have a common factor of 2, so I end up with 3 over 4. And then to find the y value, you're simply going to take the 3 over 4, or the h of t, the function value, take the 3 over 4 and replace the t in there to work out what your answer is. Okay, and that will give you the point of contact. All right, so guys, I'm going to leave you to do that, to find out what the other value is, the dependent variable. And I want to have a look at the last question for today. We're given that the following information tells us about a function f. We've got the function value, which is 4 and 5. X is 4, y is 5. And the derivative at the point 4 is 7. We want to find the equation of the tangent to f at x is equal to 4 in the form y is equal to mx plus c. So we've got the derivative, we've got the point of contact, we've got a curve. We don't know what it looks like. It can be any random thing, so I'm just going to make it look like this. Okay, and there's a point of contact obviously between the tangent and that line. To find the equation of the tangent, we need the gradient and the y-intercept. The gradient we've already got because they've told us the gradient at the point 4 is 7. So the only other thing to do is to find the y-intercept. So we're going to have y is equal to the gradient, which is 7x plus c. To find c, we simply substitute the values for x and y. So 5 is equal to 7 times 4 plus c. Okay. And so we get 7 times 4 is 28, 5 minus 28. So we get that c is equal to negative 23. So therefore my equation now, remember to always answer and give it in the form they asked for. My equation is y is equal to 7x minus 23. All right, guys, so we've gone through the typical types of questions you can get when you are asked about equations and tangents. I hope that all of that makes a lot of sense to you and you're going to continue practicing for your exams. We'll be back after this. Welcome back, everyone. Glad you came back for the wrap-up. We're going to just remind you of what we covered in this lesson. We looked at calculus. We looked at practicing some of the typical questions you get in the first 2 or 3 questions in an exam in the calculus section. We looked at limits, differentiation from first principles, and rules of differentiation that we used, and equations of tangents. Okay, so we were just able to cover a few of those in our practice questions. Remember, there's different ways that the examiner can ask you to differentiate. They can say differentiate, which is obviously meaning you need to find the derivative, or they can say determine the gradient, which implies you need to find the gradient, calculate the derivative. That implies that you need to find the derivative, determining the gradient, calculate the derivative, straightforward, asking you to find the derivative, or they can put it in as a rate of change phrasing. Okay, some of the common content skills and errors which we've covered and looked at is not using the first principles formula correctly, which there's really no excuse for because it's given to you in the formula sheet. Make sure to correctly substitute when we need to substitute values in when we find the derivative and in our limits. And be careful with your exponents and surds. And when you're looking at multi-step problems, take note of the key information. And often, as you saw, we need to use sketches, all right? If you follow all the advice, looking at your time management, mark a minute, and looking at some of those key concepts from grade 10 and 11, you are sure to do well in your final exam. And most importantly, which I did remind you about, practice, practice, practice. Where do you practice? When you're preparing for a final exam, you want to do lots and lots of past papers. So if you would like to practice further, here are a few exam papers, but you can really, there's so much there. There's so much on the DBE website, and you can find so many other exam paper questions besides these, but these are just some to kickstart your practice for the final exams. Cheers.